So here we are, part B of chapter 18, and we will continue. We're not done yet with the common ion effect and the buffers, so let's continue with those two concepts. So what are we doing now? Well, let's talk about buffers. What is a buffer? A buffer is something that is going to prevent something. It's going to diminish something. That's the basic definition of buffer in the English language. In chemistry, when we talk about buffers, we're talking about something related with acid and bases and equilibrium systems. So usually a buffer is going to consist of a pair. A pair of what? A pair of acid and base where they are weak. So you're going to have a weak conjugate acid base pair that, and this is the main thing about a buffer, that is going to resist drastic changes in pH. So what is an acid base conjugate pair? Where you can have ACl and the conjugate base is chloride, right? You can have ammonia and the conjugate acid is ammonium, right? You can have nitrous acid and the conjugate base is nitrite. So that's what we're talking about. However, it also says weak. Why weak? Because weak establishes an equilibrium. So it has to be an equilibrium system. So that wouldn't be what we're looking for. ACl is a strong acid. Ammonia is a weak base, so that will work. Nitrous acid is a weak acid, so that will work. So it has to be a conjugate acid-base pair. It could be the base with the conjugate acid or the acid with the conjugate base, but they have to come from a weak system. So you have to know your strong acids and your strong bases so you can discard those. And it has to be, therefore, because it's a weak system, therefore you're going to have an equilibrium system. So that's the main thing, and the reason for a buffer is that it prevents drastic changes in pH. So if I have a solution with a pH of 3, and I add something to it, and the pH changes to 4, that is not a buffer. pH is a logarithmic scale, so a change of 1 unit is equivalent to a 10-fold change. So that's not a buffer. However, if you have a solution with a pH equals to 3, and you add something to it, and the solution changes to 2.97, that means that was a buffer because it prevented a drastic change in pH. So that's the main definition or basic definition of what a buffer is. What about this second paragraph there? Well, let me clear the screen a little bit. So these solutions contain relatively high concentrations of both the acid and the base, because the reason they're buffer is because they're gonna prevent a change by neutralizing something. So you gotta have a pretty big quantity so you can use it without destroying the buffer. So 10 to the minus 3, it doesn't look that as a big quantity, but it is in terms of a buffer system when we're talking sometimes like acetic acid, 10 to the minus 5, formic acid, 10 to the minus 4. So this is a relatively, comparatively big amount. Or it could be 10 to the minus 2, or 10 to the minus 1, or even unit. So whatever amounts we're talking about, they have to be the smallest, around 10 to the minus 3. And they have to be approximately equal. So you cannot have a buffer that contains ammonia and ammonium where this one is 0.001 and this one is 0.010. That's not equal. That's that's like a tenfold difference. And the reason is because you can be adding an acid or you can be adding a base, and you want this system to be able to neutralize either one of them without suffering much on one side or the other. And you're gonna see, you're gonna understand this better once I tell you how a buffer works. So how can you make a buffer? Well, there's two ways to make a buffer. You need to have an acid and its conjugate base, or you need to have a base and its conjugate acid. So you can take, for example, pure water, and you can add a little bit of, let's say, sodium acetate. And you can also add a little bit of acetic acid. Therefore, you adding the acid and you adding its conjugate base, C2H3O2 and C2H3O2 minus if you get rid of the sodium, which is going to be floating around the solution. So you can add a solid, and the acid, and that will give you a buffer. And you want to add more or less similar amounts. So you want to add more or less the same amount of moles. That's what we're talking about. And they have to be a weak acid. So the weak acid would be the acetic acid, and the salt, the sodium acetate, which is going to be an ionic compound. That's one way of doing it. The other way of doing it is you can take, for example, a weak base. So I can have pure water, and I can have some ammonia in there, aqueous. And I can add a strong acid to it. So let's say that I have 3 moles of ammonia. So if I have, let's say 3 molar of ammonia, right? And I add acid to it, let's say 1.5 molar, this reaction, because I'm adding a strong acid, there's going to be a limiting reactant, which is going to be the acid, is 1:1, and it's going to produce ammonium and chloride. So that would be your balance equation. Based on what you learned on Chem 1411 about stoichiometry, when all that is done, you're going to have 1.5 molar of this and 1.5 molar of this, because this is your limiting reactant and it's all 1:1, which means your excess reactant 1.5 is going to get consumed and you're going to have 1.5 molar left. So when you do that, you're going to have your base and your conjugate base equal amount, and both of them are present, so you just build a buffer system. You can do the same with a weak acid and a strong base, consume some of this, making it into the conjugate. So those are the two possible ways for you to build a buffer. And why would you need a buffer? Well, let's say that you are doing some medical research and you have a pretty dish where you're trying to grow some bacteria that is going to produce an enzyme that you can use to inject into your patient, so it will do something with the patient to help the patient. But this bacteria, which is alive, if the pH changes too much, like ourselves, right? If our pH gets away from around 7, you can die. So the same with the bacteria, which is alive. Let's make up that this had to be on a pH of 4.5. And you're going to be adding things to it. So you want to have this in a solution, which is a buffer, that is going to prevent from this to go high or low. Because as the pH changes when you add something to it, then your bacteria will die. And you will not be able to produce any more enzyme this way. So buffers are important to control whatever system you're working on. So how does a buffer work? Well, let's go back to the one with the acetic acid. So we took our water and we added sodium acetate to it. And we also added some acetic acid. So you added that to that. So the sodium is just flowing around. And you have that in there. You got some more sodium flowing around and some more of the acetate. And then you add the acid to it. And now you're going to have your acid in there. And you're trying to add similar molar amounts, right? And now you have your buffer because you have a weak acid and its conjugate base present in the system. And we know this is a equilibrium system because it's a weak acid, right? So we took care of that. We added that. So it's already inside the solution. So this is already inside the solution. And now you're going to take, for whatever reason, you're going to take some sodium hydroxide and you're going to add it in there. As soon as you add the sodium hydroxide, you just added more Na+. So that's not going to do anything. But you also added hydroxide. So you put the acid in the water, right? It's a weak acid, so it created an equilibrium and it produced the conjugate base plus some hydronium. Your typical hydrolysis of an acid or ionization of an acid. And you have a system. Now you're going to be adding hydroxide. Now you're going to be adding hydroxide to the system. And hydroxide is going to react with the acid because so you're going to have this competing reaction happening. So you're going to produce more water and more acetate. So that means your acetate just increased. So based on the Le Chatelier principle, it's going to go that way to replenish the acid that went down. Therefore, since you have a equilibrium system and you cause a disruption to it, as long as you have enough of the acid, it will neutralize what you just added, and Le Chatelier principle will bring it back to where it should be. Therefore, not affecting the pH. And if your bacteria is in there, depending on that environment, it's not gonna even notice. So that's how a buffer works. What about if I do something different? What about if I, instead of sodium hydroxide, I add hydrochloric acid? So now, when I add the hydrochloric acid, the ACl is going to react with the water, producing that, because water is a base, right? But it will also react with this. This is a base also. So by adding the hydrochloric acid, now you're going to consume the acetate in addition to the water, so both of them will be consumed. And when you do that, that will increase the acetic acid because you are making acetic acid out of the acetate and the ACl, and that will cause the equilibrium to go that way. So when this came down, so the pH was the hydronium was consumed, and that will force it there to bring the hydronium also that way. So the fact that the buffer contains an acid and its conjugate base allows you to add a strong acid or a strong base, and one of those two substances on the conjugate base pair will neutralize the acid or the base, therefore preventing a change of the pH. So that's how a buffer works. So let's look at this problem. Determine whether mixing each pair of solutions results in a buffer. So by mixing this, are we gonna get a buffer? Quick review. What is a buffer? A weak acid with its conjugate base, or a weak base together with its conjugate acid. So what this is asking is, when I combine those two substances on A, B, or C, do they give me a weak acid and its conjugate base, or a weak base and its conjugate acid? So let's see. For the first one, we are mixing together ammonia and ammonium. So do we have present a weak base and its conjugate acid? Yes, we do. So that's the main requirement. You have a weak base with its conjugate acid present. Are their amounts very close, very similar? Well, this is going to be 0.1. This is going to be 0.15. The amount is the same. So it's, I would say, pretty similar, 0.10 to 0.15, given that the volume is the same. So yeah, the amount is similar. And what else? And that's it. So yes, the first one will give us a buffer system. No questions about it. What about the second one? The second one, let's see what we have. We have a strong acid and a strong base. No, that's never going to give us a weak acid with its conjugate base or a weak base with the conjugate acid. What about the last one? The last one, I have CH3NH2. That's going to be a base. Why? Because if you do the Lewis structure for this, you're going to come up with something like this. And that lone pair can behave like a Lewis base. You can donate that lone pair as a Lewis base. And if you do that, a Lewis base will accept a proton, giving you its conjugate acid. So is that what we have? Where we have the base and its conjugate acid right there, right? So we're gonna have CH3NH2 and its conjugate acid, which is CH3NH3 plus. And I know that because I know this is Cl negative, so this has to be plus. So yes, we have, and this is not a strong base. A strong base has to have hydroxide and a metal from group 1 or group 2, except beryllium and magnesium. So this is a weak base with its conjugate acid. Are the quantities more or less similar? 0.15 molar, 0.25 molar. The one with the lower molarity have a higher volume. So I would consider those to be within the same broad range. So yes, this will also be a buffer system. So that's how you determine if you have a buffer system or not. So here's your daily work. Let me see if there anything here that I need to reemphasize. Pay attention to this one. This one, you have HF, but you do not have F negative anywhere. However, this is an acid, and you're adding a strong base. So this is one similar to the one we did earlier, where some of the acid reacted, producing a given amount of the conjugate base. So C is the resulting quantities based on the stoichiometry are going to be similar to it. That's what we did. That's what we did in this explanation here when we were talking about how does a buffer work. And here you're going to have a base, and you're adding a strong acid to it, which is going to consume some of the base, creating some of the conjugate acid. See if at the end you have both present, the base and the conjugate acid. So be careful with those. Make sure that you keep in mind stoichiometry, limiting reagents, and so on. And with that, we come to the end of this part. So when we come back later, we will still be working on these two concepts. So we are not done with that concept yet. So see you next time. Take care.